Hi guys, I'm Sneha S from Sri Venkateshwara College of Engineering, Department of CSE Cybersecurity, studying in third sem. Today we'll be dealing with two topics that are BCD counter and map method, which is from digital design and computer organization. So let us begin. Contents we are going to study today are map method with example and BCD counter. So map method, which is also known as map or K-map, which is a diagram made up of squares, and each square represents one min term of the function that is to be minimized. So basically, what is map method in the sense, whenever a function is given and you have to minimize that particular function. So you use this method called K-map, in which functions are minimized. The simplest expression produced by the map are always in one of the standard forms, that is sum of products or product of sums. It will be assumed that the simplest algebraic expression is that has a minimum number of terms with the smallest possible number of literals in each of them. So you must be wondering that why are we even minimizing these functions? So whenever we design circuits that are ICs and all, we usually we all know that we'll be using basic gates. So when we are using this basic gates, we have to minimize their number. So in order to minimize their number, we'll be using the map method, which will give us, like, even if you use many gates and simplest gates, we will be getting the same result. So in order to minimize that, the use of gates, we use the map method. So first we'll be studying two variable K-map. A two variable K-map is shown below. It has four minterms, that is M0, M1, M2, and M3. So it contains only, it can only give numbers, that is 0, 1, 2, 3. Each of which has a minterm. Uh, we are representing it in a square box. Now the number is 0, 1, 0, 1. So whenever you have to represent 0, it will be x bar, y bar. For 1, it will be x bar, y. And for 1, it will be again x, y bar. And for again 0, it will be x, y. Uh, so when you are representing only x, y, you will be putting a number 1 in the M3. And similarly, if you have to put x plus y, so you'll be putting 1 in x and 1 in y. Three variable K-map, they have 8 minterms. These are used for three variables of 8 squares. Minterms are arranged not in a binary sequence, but in a sequence similar to gray code. So here it will not be like a gray code means, instead of now, usually the numbers will be represented in binary code like 0, 0, 0, 1, 1, 0, and 1, 1. But in gray code, it will be 0, 0, 0, 1, 1, 1, and 1, 0. Since it is for three variables, there will be 8 minterms, which can be represented in the order of M0 to M6 or M7. Each square represents one minterm, giving a term with 3 literals. Two adjacent squares represent a term with 2. 4 adjacent squares represented with 1. And 8 adjacent squares encompass the entire variable, which is always equal to 1. Which means when you are using where you have grouping can be done in three ways. Either you group 2 or 4 or 8. So whenever you're grouping 2, you get 3 variables. When you're grouping 4, you get 2 variables. And when you're grouping 8, you get 1 variable as a simplest equation or expression. Let us see 4 variable K-map. Here you'll have, since there are 4 variables, you'll have 2 to the power 4 minterms, that is 16. And each square represents one minterm, giving out 4. If there is only one minterm, then it will give us 4 literals, that is 4 variables. And if there are 4 adjacent squares, it will give us 2 literals. If there are 8 adjacent squares, it will give us 1 literal. And the 16 adjacent squares means if your grouping is in such a way that it has grouped all the 16 adjacent squares, then it is going to produce a function which is always equal to 1. Here is an example. Here we are solving this equation, function which has 0, 4, 0, 2, 4, 5, and 6. So firstly, when since it's a 3 variable K map, we have to draw 8 minterms, and M0 will be equal to 1, M2 will be equal to 2, and M4 will be equal to 4, and M5 will be equal to 6, and M6 will be equal to 5. Means here it is in the order of 0, 1, 2, 3, 4, 5, 7, and then 6. So wherever these numbers are present, you'll be writing 1 there. Then the grouping starts. Here the grouping can be done in 2 ways. The first way is they have grouped 4 by taking M0, M4, M3 and M6. Now since there is grouping of 4, it will produce as one function, that is Z bar. And the second one is M4 and M5. Since the grouping is done only between 2 squares, it will give us 2 variables. Here we have to check out the common variables. Since Y bar is common in M4 and M5 and X is a single literal, we write it as XY bar. This is how you solve a simple K map. Now let us see BCD to X is 3. So BCD to X is 3 means BCD is a binary code, but in order to produce a XS3 code, we simply have to add 3 to that particular number. So it contains 4, it is actually BCD to XS3 has a 4 input variable and 4 output variables, namely ABCD, WX and YZ. It has 4 bit, so the 18 combinations possible, but only 10 will be listed and the 6 other are don't care conditions. An XS code is obtained from the corresponding binary value plus 3. For example, the binary code for 2 is 10, but the XS binary code for 2 is 0101, which is 5. So we have added 2 plus 3, which is 5, and therefore the binary code for 5 is 0101. But in XS binary code, it will be giving the value for 2 as 01 and 01. Now let us see the truth table. Since I already told that there are 4 variables, we'll be getting 8 combinational minterms, but we'll be listing only 10 because the rest 6, that is 10, 11, 12, 13, 14 and 15 are don't care conditions. So it is not necessary to list them. So the first one is 0000. But in the output we get 0011, which is the binary code for the number 3. So ABCD are the binary codes for 0 to 9. But here in the corresponding, we have given the binary codes which are XS3. So 0011 will be corresponding to 3. 0100 will be corresponding to 4. 0101 will be corresponding to 5, and so on. And the other don't care conditions are not listed here. This truth table has to be represented in the K map. Like for the first we'll take W, our W, that is 00001111 and 1. So now it will be corresponding to 3, 4, 5, 6, 7, 8, 9, 10. So wherever this corresponding numbers are there in this 4 variable K map, we'll be writing 1 there. And for don't care conditions, that is 10, 11, 12, 13, 14 and 15, we write X. Similarly, X, Y and Z are represented in the corresponding K maps. And in the first case, while taking the W, we are we can include the don't care conditions while mapping. So we have taken 4 minterms or 4 minterms. These 4 minterms are taken like 8. Therefore, the only variable that is not changing is the constant one is D bar. Therefore, Z is equal to D bar. Next for Y, we have done grouping in such a way of 4 grouping, where so we got the literals in 2 variables. Next, the grouping is done in 2, 4, 4 and 2. Therefore, we got B bar C, B bar D plus B C bar D bar. Similarly, for W, it is done in 8 and 4 and 4. Whenever we are combining 8, we get 1 variable. Whenever we combine 4, we get 2 variables. After using this truth table, we have designed this, and the simplified equations are represented using the basic gates. So we have taken 4 variable input, that is ABCD, and outputs WXYZ. For Z, it is Z. The output is D bar. So we have taken an inverter. For Y, it is CD, C bar D, which is CD plus C plus D, C plus D, the whole bar. So we can do this by using one AND gate and one NAND gate, and combine this using a NOR gate. Thirdly, we'll see X. Here we have used the simplified equation is B bar into C plus D plus B into C plus D. So we have to use a NAND gate and two OR gates. And next one is W. For W, we are using one OR gate, two OR gates. Actually, we are using two OR gates, which will give us the output for W. This is how we do BCD for XS3. That's all, guys. Thank you for watching. Please like and subscribe to my channel.